so we did we already started some part of today's lecture. So let's refresh some of them. Okay. So yesterday we asked this question. So first, okay. So we know this. For any other miscible flag. Okay? And I didn't state this yesterday, but this is also equivalent. For any f. Okay. And the real this is known. The question is whether with the last one with a fixed point. Okay. So we will have the answer for this question. So for any pullbacks are also numerically equivalent. So this means even if we put f pullback here, this is also true. And what we are going to ask, what we are going to answer is actually this one. So it's a little, we have to modify a little bit when we come up with the real answer to this question. Okay, anyway. And also let's record the divisor letters. So for pseudo effective divisor D. So this is D T plus N, where this is the asymptotic order of D along E. Okay. And this is just D minus N. Okay. And I explained that there are only finitely many prime divisors whose asymptotic order is positive. So this is a well-defined divisor. And this is called the negative part. And this is called the positive part. Okay. And this is, so dimension is larger than or equal to 2, and the dimension is denoted by n. And this definition works in any dimensions. Okay? But in dimension 2, there is only one definition of Zariski decomposition. But in higher dimensions, but this is not the only Zariski decomposition. You have many variations of Zariski decompositions in higher dimension case. And this is just one of them. Okay. And in dimension 2, P is nef, but in this case, P is only movable. And nef in dimension 2 case. Okay. So we will use this to have an answer in this question. Okay, so we note this note. So when D and D prime are numerically equivalent, then we know that P is numerically equivalent to P, and N is just the same. So T plus N is the statistic decomposition for D, and P prime plus N prime is the divisorial statistic decomposition for D prime. Okay? So P is actually defined up to numerical equivalence, and N is just the negative parts are just the same. Okay? So this is because this function depends only on the numerical class, and not the divisor. Okay.
Question about possibly recurring division. So, is it true that if you take the relative position of G and then take another divisor, say H, very divisor, very general, and say general in this linear system? Is it true that if I restrict the left hand side and the right hand side to H, I get the relative position on H?
You mean the restriction? So whether this is the statistic decomposition.
Yes, no question.
And H is very general. You said.
Say general in some variable.
Very ample. Yeah, I suspect it is true, but I have to check. I don't know. Yeah, I suspect it's true. So all you have to do is whether
Restricted to H is okay, it is movable, right? Because P itself is movable. And H is general, so it doesn't pass through.
Yeah, I think it's true. Yeah.
And N is perfect.
Yeah, I think if H is sufficiently general, I think it's true. Yeah. Okay. Yeah, so this is because order of E, D is order of E. So this function is a numerical function. So N is just the same, and if you just subtract from this the same divisor, you of course get the same numerical positive part. Okay. So you just have to modify this. Okay. So here is the definition. We say D X and numerically equivalent. I forgot. Near H, near X. So okay. D and D prime are numerically equivalent near X. Okay. Okay. So we consider the divisorial statistic decomposition. Okay, so D plus N, D P plus N prime. So these are the statistic decompositions, and if P and P prime are numerically equivalent, and N X and X prime are the same. Okay, so I will explain what this is. So if you have the negative part N, and we further decompose. Okay? So C stands for the complement. Okay? each component contains the point x, and about this, x is not contained in the support. Okay? So you just collect all the components from the negative part, which contains the point x. Okay? So this is the numerical equivalence near the point x. Okay? And d equal plus nx, c is called the refined divisorial Zariski composition at x. Okay. So to define this, you first find the refined divisorial Zariski decomposition at x, and your negative, positive part should have the same numerical equivalence, and nx and nx prime must be the same. So actually, this is the answer. Okay. So here is some properties which are easy to prove. Okay. Some lemmas. So 1 d is equal to a if and only d for x. Okay. So yesterday I explained CD, DC for any C, and DC prime for any C containing X. They define the same numerical equivalence, but this is different. Okay. So I explained this was a wrong guess, and this is the right notion, I think. Okay.
So basically you ask something global of P, right? In this definition.
Global of P.
Something global of M.
What do you mean?
Well, okay, it doesn't make sense to argue with the definition, but still, so you really require that the positive part is the same even far away from X.
Positive part is far. Yeah. Positive part is just the same numerical equivalence. So definition comes from this. So you want this to be true only at x. So we leave this. We don't touch this part. And for this part, we just want the components containing x to be the same. This is the only difference.
But for instance, it's not equivalent, the definition is not equivalent to requiring that the intersection numbers coincide for every curve passing through X. It's something different.
So D prime C requiring X. You're saying this? So yes, no, this is the same thing as this.
Oh yeah, sorry.
Yeah. So this doesn't mean anything. Yeah. So these two are the same.
So the new definition is
Different. So just by definition, this is obvious. And this is actually also easy if you consider all the points. Okay, because But so this part is obvious. So how is it? So this part is, so if you want to fix a point x, d is p prime plus n, x plus nx complement p prime. No. P prime, p plus nx prime, ncx prime. So if you want to fix a point x, then we know that nx is nx prime. But we want to show that this is also equal to each other. But consider x n minus nx. So just nx nxc. But it's almost obvious. So if you want to fix a point x, you know that nx and nx prime are the same, but you want this and this to be the same. So you just consider the other points which are not contained in here. Then you see that the components of n containing x will have the same coefficients. Okay. So if I say more, I may confuse you. So if you know the definition, it's almost obvious. And two, what's so this also comes from the usual numerical equivalence. So if d and d prime are numerically equivalent, then d for any bidirectional motion. Okay. So we want to have this property as well. So d. So actually, so this is just an easy observation. The next one is actually a theorem. So the following are equivalent. D and D prime are numerically equivalent near x, and P. So this is okay. And next one is for any x containing B. So B is a irreducible subvariety containing x. Then order V, D is order V, D. So this says that here we recall this fact, B minus D is actually the union of V, where order V, D is positive. So this is one fact for B minus. B minus is the order union of the irreducible subvarieties whose order is positive. Okay? So this means that if D and D prime are numerically equivalent near x, then this is from the definition, but this says B plus B minus. So if you compare these two non-F locus, then like the divisorial case, if a component here contains x, then there is also a component here. If there is a component here containing x, then there is also a component containing x. Okay. The next one is I just erased, but this says f full bet D is also numerically equivalent to for any f y to x, and x prime is mapped to x. Okay. Okay. So I will not prove this, but it's not too difficult if you think, if you understand the definition. Okay. So using this, so I will come up with an answer for this. Maybe I can use this. Okay. So now we have a theorem. And this is by CP Park 1, and actually this is done by Joachim Roy in dimension 2 case. And the following are true. 1, D and D prime are numerically equivalent near X. So actually this is the answer for this. Yes. So this comes here. So for any D prime, for any infinitesimal flag y1 over x. So infinitesimal flag means you have a bidirectional morphism from y to x, and you have a flag here. Then all the flag collapses to x. So this is called the infinitesimal flag. Okay. So all the components in the flag collapses to x. But 3 and 4 says you don't need to consider all the infinitesimal flags. It's actually enough to consider some subsets of this. Okay? So there are actually 2 types. So which one was first? Sorry. I switched order. So this comes later. So let's switch the order. Okay? So actually, the first part are the same. Again, same. Okay, so the first one is just for any flag y1 y such that f pi yn is x. Okay, and for any infinitesimal flag y1 over x. And the third one is proper flag. I'll explain these flags. So I may have said a few times, but so if you want to extract some properties of D, then you have to, this is the only option you can vary, okay? So the principle is you have to come up with a nice flag which catches the properties of D, okay? So this is what it does, okay? So, so first one is any flag. So let's have x prime to x. Okay, the first one is y1, y2, y3, and yn. The first one means this one just goes to x. Okay, so we don't care about how this collapses. Okay, the first one is as long as the last one is mapped to x, it's okay. The second one says the y1 collapses to x. Okay, and the third one is y1, y2. This also forms a flag. Okay, nothing collapses. Okay, so this is the largest subset, and these are the subsets of these. Okay, so 3 and 4 sets, you don't need to consider all these. You only need to consider some subsets of flags. Okay. So this case is proper. Okay. So if and if y1 is mapped to x, this is infinitesimal. Proper means it just goes down to a flag. Yeah, so yeah.
So not proper flag is infinitesimal, and no infinitesimal flag is proper.
Infinitesimal means all these collapses to x. But proper means it doesn't collapse at all. So y1 goes to the codimension 1, y2 becomes codimension 2, and it forms a new flag.
But it just means that nothing except the last, except yn is contained in the exception divisor, right?
Which one?
It just equivalent to saying that yn minus 1 is not contained in the exception divisor.
Yn minus 1 is contained. Yeah.
And then it will follow that all the other parts of the flag will be here. Can I also the following question? There's also one more obvious small subset inside infinitesimal flags. Your exception divisor is going to be a vector space. So inside the vector space you have obvious nice flags, right? Those that can consist of vector spaces. So maybe,
You mean?
I restrict myself to the second place.
I'm sorry.
Let's restrict ourselves to the flags that have two properties. First, they are infinitesimal. So it means that they are all contained in the exception divisors. The exception divisor, right? Y1 is the exception divisor itself. Y2 is subdivisor there, etc., etc. Suppose that all the members of the flag are linear subspaces in the exception divisor.
Yes.
Will give enough information.
Yes. That one is also useful. That one you also consider.
And do you have like some physical equivalents? Do they detect?
Yes. Actually, yeah. So So actually, so first you have a flag, and you lift it to a new flag, and you intersect with the exceptional divisor, and you get another kind of flag. Right? That's what you are talking.
Okay, but with different flags.
Yeah.
Because for instance, the first place you take not the exceptional f y1, but the exceptional divisor, you take e itself. I just want to consider the family of the following simple infinitesimal flags, such that y1 is almost e itself.
So this is y1.
Y2 is some linear subspace.
So it's
like b and minus 1, b and minus 2, right?
E intersection something, right? You're saying.
Well, of course it's going to be an intersection with something, but I just mean that E is a projective space, right? E is a small projective space. And I want Y2 to be a linear subspace of this projective space.
Linear subspace or projective space.
Yeah. So E is a subordinate of projective space, right?
Yeah.
If I got it right. So pi is just a block of point.
Why?
Did you mean that pi is a block of point? Pi.
Yeah.
It's just a block of point. And that's the given derivation.
Actually, it doesn't have to be a block.
Then what is pi?
So any birational motion.
So we fix it from the very beginning. Or we also override everything over rational motions.
So we vary the morphism pi. So actually for any pi.
Sorry. Yes. So the second condition is that for every pi, the following requires right? For every pi, every flag with this property. Okay, then my question is, let's restrict to one particular pi.
One particular pi, yes.
For pi, let's take just the blob of our point x.
So pi is the blob.
Just the blob of our point x. So we check just for this particular pi.
No, fix, yeah.
Yeah. Will it be enough?
Is this enough to catch this one?
Yeah.
Just one.
Just the usual level
Just one blow. One blow up. Just one blow. So with just one blow. I think it's enough. So yeah, actually, this is too many. There are too many. So actually, yeah, I think it's enough to have one blow.
to check not for every pi, but just for one.
The one pi, yeah.
And then it means that my previous question starts making sense. So my previous question was like this. So let's fix pi to be just below 1. Then our exception divisor is a projective space.
Projective space.
n
minus 1.
And let's consider the following family of flags. They will all be infinitesimal. Y1 will all be e itself. y2 will be some linear subspace.
Yes.
Not an arbitrary.
Yeah.
Subspace. And e3 will be linear subspace there. So just take the flex in the usual sense in the linear space. So will this be enough effect?
You mean for one particular blow, for one particular flag?
Not flag, but some subfamily of flags. So you will you take all possible.
Y1 is fixed, but Y2, Y3 are.
Yeah, they're just linear subspaces.
Many.
Not arbitrary.
Yeah.
Right? So linear subspaces. Will this be? Why one is fixed? So let me take your condition 3. Yeah, we're speaking about generalized condition 3. Why one is fixed is consequence of this event. For every reflect, why one is fixed. Right? So the question is, can I make it linear?
Can you make what?
Well, I mean, can I make all other subvarieties linear subspaces? Exactly. The final dimension, right?
Yeah, I think it's possible. Yeah, so anyway, 2 is just, so we just consider all the possible flags over it. But this just says this is, you don't need to consider all these, just need to consider subset. But actually, this may be also more than enough. Okay. Okay, so I just sketched the idea. So this is so as I said, so in 2 we consider all the possible flags of this type, but 3 and 4 says you don't need to consider all of these. You just need to consider some subsets. So I'll just demonstrate how to show 1 and 2 are equivalent. So I'll just sketch briefly. Okay. So pi is variational morphism, and y is so flag. The flag is of this type. Flag. So we say centered at x. So this means y1, yn, pi is x. Then pi curve d is p. So we consider the refined divisorial Zariski decomposition. Okay. So x, let's put g plus ng. So g is mapped to x at any point. Okay. So from this property, so we still have the numerical equivalence near g. So this means p and p prime are numerically equivalent, and ng is equal to ng prime, but we don't know about this. Okay, so we consider so actually this should come first, but yn is g, so we let this equal yn. Okay, So if we consider the divisorial 자리식 decomposition for pi fullback D, and we know that this splits into the sum of the 자리식 Okounkov bodies of each piece. P plus N X N G plus NG complement. Okay? But Yn, the center is G, so actually this divisor is completely away from the flag. So this is just a 0. And this may have some evaluative point, but this is some point. So a zero-dimensional point. So this is just a translation. Okay? So about using this fact, Okounkov body is the numerical property, so we can replace this by P prime. And we know that this divisor and this divisor are the same. NG prime. And again, NG prime complement is away from the flag. So this is just this part is again 0. So if you sum up all these, you get Y pi fullback D prime. Okay? So this is how you get 2 from 1. Okay? So from 2 to 1 is also not typical. So obtain N and then P. So you find N first from this information. So let's say, so the idea is this. So suppose you have y1 plus some negative part. So this is the negative part. And suppose you have y1 in the negative part, negative component. Okay? Then your Okounkov body looks like this. Okay? So this, so when you look at the first axis, the distance from the second, how do you say? I mean, the distance, you project this onto the x-axis and the distance from the origin. So the first point actually corresponds to this number. Okay? Okay? So if you, so by letting pi the identity and you consider all the prime divisors for y1, then you can actually obtain all the coefficients from the Okounkov bodies. Okay? So this is the idea on how to obtain the negative part from the Okounkov body. Okay? And P, for P, we can also obtain. P is for P, for negative part, enough to find PC, the intersection number from the Okounkov bodies. But this is hidden in the last axis. So suppose you have the Okounkov body, which looks like this. Then if you look at the last axis, so this corresponds to this. Okay. Okay. So in the last axis contains the information of the intersection number. Okay. So this is the idea. Okay. To obtain the numerical class of P. Okay. Okay, so we have answered this question now. Okay. Okay, so from in two we consider the bidirectional morphisms. But what if we don't blow? So it's like the similar situation with the Sechadel constant. If we blow, you get the exact Sechadel constant. But if we don't blow, we only get the bound, lower bound and upper bound. So in two, so what happens? This is what happens if we consider y1 on x without blowing up. Okay, so the following are equivalent. One. So we have two divisors, d and d prime on x. Okay, so this is given, and so p stands for the positive part, and n stands for the negative part. Okay. So p and p prime are numerically equivalent. X smooth, and x prime smooth, and x singular. So I will explain what this is. Two. So in this case, we don't blow. For any flat at x. Okay. So this is the actual answer for our question. So because we didn't blow. So if we blow, we get the precise numerical equivalence near x. But if we don't blow, we get some less information. So I explain what this is. Okay. So these are the this is the subdivisor of the negative part, which contains the point x. Okay. So we further split this into two parts: the smooth divisor plus the singular divisor. Okay. It's a smooth part and the singular. Okay. So what this says is, you still get the same numerical class for the positive part. And for the negative part containing x, you precisely get the same smooth part, but for the singular part, you get the same Okounkov body instead of the same divisor, because this is weaker than singular. Sorry. And x prime singular. So So this is weaker. So this implies this, but this doesn't imply this. So we get something weaker information if you only consider if you consider the flags only on the device, only on the variety X. Okay. So of course this is natural. So because we consider more flags, but this we consider we consider less flags. Okay. So the one is actually weaker than this. So this implies this, but this implies that. It's a little bit weaker. So if the divisors are the same, we are happy, but in this case, we only get the same Okounkov body, which is weaker than this notion. Okay. So far we only consider the positivity of divisors. So we didn't talk about the global geometry aspect. Okay. So we have about 30 minutes, but this some parts overlaps with my research talk I gave during the 2-day conference. But let me briefly explain. So this, so until now, until here, we only consider the positivity. Okay, so we always wanted to find some nice applications in the geometry. So I think this is the first application. So F from, so let's start from X, Y. It's a fiber space. This means surjective and connected fiber. Okay. And F is a general fiber. Okay. And so this is called the product formula. Okay. And let's assume all the varieties appearing of general type. X, Y, F are general type. Then this product formula says the volume Kx, let's say the dimension is D prime, and D double prime. Okay, so these are the dimensions. Okay. Dimension D, just D factorial volume of Ky, D prime factorial volume Kf, D double prime factorial. Okay. So this was originally proved by Kawamata and so you can also find this statement in Tsuji's paper. Okay. So if you see this volume divided by D factorial, something should come up in your mind, in your head. So this is actually the volume, Euclidean volume of the Okounkov body for Kx. Okay. This is actually the Euclidean volume of Kx. So Okounkov body of some flag Kx. Okay. So you can interpret this statement in terms of Okounkov body. Okay. So I'll just explain the. So it's not proof, but again, the proof is done by choosing some nice flag. If you choose a nice flag, then the proof is automatic, almost automatic. So use a fiber type flag. So you have you have a fibration from X to Y, and you have a first you F D, so F1, F2, so this is the flag. So this is flag on F. You first find this flag, and you complete it. So this is still in X. Everything is a subset of X. So you complete this to a flag on X. So X1, X2, right? In this case. So now this is a flag. X flag on X. And this should also satisfy one more property. So you push it down by F, and then you have Fx1, Fx2, Fx. So we want this to be Y1. Y2. And this must be YD prime. Okay, so this is D prime. Okay. So this is Y. Okay. So if you fix a flag on F, you complete it to a flag on X, and this should satisfy these properties. Okay. So once you use this flag, then you get automatic. So what you get is the following. So maybe flag Y. And if you use this flag, then what you get is Okounkov body of Y cross F. FKF becomes a subset of KX. So this means let's assume that this is one-dimensional, this is one-dimensional, then this is two-dimensional. So you get the one-dimensional Okounkov body. And you get the one-dimensional Okounkov body. You cross product. Okay? And then you get this square type. Square. Okay? But on this side, this says this Okounkov body is bigger. Okay? So once you have this picture, you find the Euclidean volume. The Euclidean volume of this is the length. Euclidean volume of this is length. And if you the length times length is the area of this, but the area of this Okounkov body is larger than this, okay? Because this contains the box formed by the base and height. Okay. So actually, this is not. This is just one small application, and then, but. So what I want to say is, so by now, this contains more information than just just the volume. Actually, just the. Okay. So the volume corresponds, the Euclidean volume corresponds to the volume of the divisor. The dimension corresponds to the Ithaka dimension. So this contains many information, not just this. So my question is, yes. Fiber type. Okay. So why is this meaningful? So there is some conjecture called the Ithaka conjecture. So Ithaka conjecture says, so when we have such vibration, kx, ky plus kf. Okay, so this is the Ithaka conjecture. Okay, but so this is solved in many cases. For example, f is general type. F is good minimal model. Good minimal model. Or f y has maximal Albanese dimension. And there are a few more cases where this is solved. Okay? So why is this meaningful? So let's assume this is true. Then this automatically means this. But we get some extra information. We get some extra information about the product formula. Okay? Because this doesn't tell you not just the dimension. This also tells you the volume of the divisor. Okay? So this is a mixture of Ithaka conjecture and the product formula. Okay? So this inclusion makes sense even if this part has a smaller dimension. Okay? So this question actually implies this. So of course, from here, we don't assume this generality. So this is only in this theorem. This is for any fiber type, any fiber space. Okay. So I want to see whether we can solve a new case of Ithaka conjecture using this, but I should work on this. Okay. Any questions? So far, Okounkov body doesn't have many nice applications. It only has some deep theories so far. Okay, so I hope this helps us at least to understand more about this conjecture and you get some more extra cases where this is true.
Question. So, in this proof form, we require X, Y, and F general type.
General type.
And in this first case, where we have compared we just require F general type, nothing more.
F is general type.
So you don't require anything in X and Y.
You mean you're asking this about this?
Yeah.
This is where this is already solved. When F is general type, we know.
The assumption is in this solved case, just F general type, and nothing wrong.
Nothing wrong. Or, and even more generally, good minimal model.
And still nothing wrong.
Nothing, just this.
And in the third case, the requirement is only for Y and not
Yeah, only for Y. Yeah. These are all independent. Yeah. And there are a few more cases. I think this is also okay. Sorry?
I think there's also.
Yeah, there are some dimensions, yeah, particular dimensions where this is solved. Yeah. And actually, if you put the numerical dimension, this is also solved. Solved. So this means if you assume abundance, then Itaga conjecture is true. Yeah. But people suspect that you may not need abundance, but I don't know. For why is general type? I think this is also solved, general type. If Y is general type.
Okay, what do you consider the, so to say, minimal non-solved case?
Minimal non-solved case. What does that mean?
What's the reason in the general case does not get approved?
I mean, what's the so you're asking what should we do next?
Some other trivial case when you have some minus infinity somewhere.
So you're asking what's the next step?
Yeah.
I don't know. Actually, I was more interested in this. So I was suspecting when this is equal, then we may have this. But so far, actually, I'm not. Yeah, I'm thinking about this too, but I'm thinking more about this. So I don't know what's the next. Yeah, so you're asking what's the next easiest case? I don't know.
Say what's a family situation you should have? You must know that F is a minimal, right?
F.
What's the reason the family arises? We should not know.
Yeah. I don't know. Yeah, actually, if you're interested, you can work on this together, maybe. Yeah. So anyway, so this contains a little more information than this. Okay? And this tells you something about the product formula, because the Okounkov body contains not just the dimension, it also contains some information about the volume. So anyway, I think this is an interesting question. Okay. So I have about 15 minutes, but so next, so I cannot say much about this, but so next application is about the the Nagata conjecture. So this is done by another Korean guy independently. So I will just briefly introduce. So we already defined this. So this was the supremum of T fullback of A minus TE net. Okay? So this was the 1-point Shadel constant, but there is also multi-point Shadel constant too. So A, x1, x2, xr is the supremum of. So you blow up all these points and you get R exceptional divisors. Okay, T 5 fullback minus T E1 plus ER is net. Okay, this is called the multi-point Shadel constant. Okay. And Nagata conjecture says so so x1, xr are general points. P2. Okay. And then epsilon. General point. So just a line. Line H1 XR. So and R is large. Then this is equal to 1 over R. So this is the conjecture. So it's surprising to see that even about P2, this is unknown. Okay. So this means that actually, if you see from this definition, so you see that epsilon are the Shadel constant H. So I'll just put so let's put x2, xr. So this upper bound is easy to obtain. Okay. So because you see this is still big. Okay. Okay. So if you use the bigness, and if you square this, so pi perfect H E1 ER, and if you square this, you still get positive. But if you see 1 plus t squared, these are minus 1 curves, so you have minus r, and this is positive. And if you solve this, you get this upper bound. Okay, so this means that this Shadel constant attains the upper bound, precisely the upper bound. Okay. So you can interpret this in terms of the Okounkov body too. But of course, you have R bases. So actually you have to have R different admissible flags. So you have to have some complicated Okounkov body, but you can still rephrase this using the Okounkov body. Okay. So I just explain this briefly, so you can look up in the archive. So over each xi, there is infinitesimal over xi. So over each point, there are infinitesimal flags. Okay. So using this, the multi-point Okounkov body. Okay. Y1. Sorry. So let's put I here. Okay. Y1, Y2, YR, D. So let's try to prove it. Okay. So how do you do this? So so you take an effective divisor from this, and you evaluate this effective divisor using this is actually RNR. So this is new Y1 D prime. So this is N. So you have R of these, R pieces. Okay. Y2 D prime. And the last one is Y R dot D prime. So this is a point in this space. And you collect all these points and you take the convex closure and you get this Okounkov. Okay. So this is a huge Okounkov body. Okay. So this is called extended Okounkov body. Okay. So using this, you can interpret this. So this is actually theorem. The following are equivalent. 1, Nagata, conjecture holds. 2, so this is so in the 1 point case, we already defined this. So in dimension 2, so inverted simplex of size d, size delta was this, and in higher dimensional case, you consider this. So E1 plus E2, E1 plus E3, 0. So convex flow of these points is the standard inverted simplex. But this is the generalization of this inverted simplex into this space. Okay. So this is contained, and I also, this is the size, but this is where you change this to big. So this is the supremum of T, pi pullback, what was it? H or F. Here we have H, so it's H. H minus T, E1 plus ER is big. So this is the Fujita-Nakayama type constant. Okay, the inverted simplex in this space with size of size mu. So this is contained in y1 dot y2 dot yr pi pullback. Okay. Okay. So maybe for now it may be hard to grasp the meaning of this, but anyway, the point is many questions regarding the Sechadel constant can be rephrased in terms of Okounkov bodies. Okay. So only recently I started to see some applications of Okounkov bodies. So I will not state here, but even K stability. So Ivan already talked about this a little bit, but so here you have to, it's important to compute the volumes. But to compute the volumes, so knowing the Okounkov body is sometimes useful. Okay, and also if you, Okay, so I started seeing some nice applications just recently. Okay, so I only have 5 minutes, but it's a summary. Let's see. So let's just a summary. I have a summary in maybe 3 minutes. So for divisor D, we can define some D, the dimension of X is D. Okay? And we want to extract as many properties as possible from this convex geometry. Okay? So the volume, Euclidean volume, corresponds to the volume of D. Okay? And the dimension corresponds to the numerical dimension or the Ithaka dimension. Okay? And what else? The edges from the origin. And they say something about the Sechadel constant. Okay? And what else? Well, the neighborhood of 0 is contained in O. Then this is nef or empty. Okay? And yeah. So this is not precise correspondence, but if it contains, yeah. Okay. And you can ask many other questions. For example, so let's say you have, this is the x, so you can have many questions. For example, so let's say this is your Okounkov body. And so edges mean this. Right? They give you actually lower bound and upper bound. Okay? Sorry? And you may ask, so the whole volume corresponds to this. So you may ask whether the sections on each space mean something. Or you may ask whether these, the number of points, the number of vertices mean something. Okay? So you can ask various questions. And I don't know the answer to these questions for now. Okay. Yeah, so okay, so okay, so I finish. Yeah.